Pleasure to be here. It's great. On the MSU chemistry department page, when I pull up the faculty, there are 5 or 6 people in a row that have been part of my life over the years, and so it's a pleasure to come back and visit with people that went to Princeton with me, or were students back when I was a faculty at UMass, or have won the Presidential Green Chemistry Challenge Award. So I think this is the first time that I've ever actually been here to MSU, and hopefully it's not my last, and this is a great opportunity to come and talk to you about something that's very near and dear to my heart. What I want to do today is talk about the subject called green chemistry, which sounds like an oxymoron to people that are not in the field of material science and chemistry. But hopefully, as people in this room are very much engaged in material sciences, you understand that that isn't so. We live in a very polarized world, and everyone has their own way of looking at things. The first thing I always like to do is to have a disclosure that I have no presumption that I know what I'm talking about. You know, I don't say to myself, this is the way the things are and you must listen to me. Okay, I have lived my life and have come to look at the world the way I do, and I'll share it with you. And if you like it, great. And if you don't, that's okay. I spent 10 years in industry working at Polaroid. I spent 10, 11 years as a professor teaching at UMass. Spent the last 10 years as an entrepreneur running a startup company. Through all of these 30 years, I've been engaged in chemicals policy, working with the federal government. I testified to the House and to the Senate on TSCA reform, worked with the European Union on REACH legislation, served in the Schwarzenegger administration in California in chemicals policy. So I tend to see things in a very systemic way. I look at the inventing of things, the making of things, the doing of things, the teaching of things, and the managing of things all kind of go together in a certain way. And so my perspective comes from that background. And like I said, I have no presumption that I've got some gifted insight. It's just the way that I look at things. Obviously it seems that this is becoming more and more so that in our society, everything is hyperpolarized. Everything has to be a shouting match. When it comes to chemicals, it's really, really bad. You open up the newspaper, you turn on the radio, you look on the internet, and you hear about this thing is toxic, this is bad, this is killing us, this is dangerous, this is bad, this is scary, we're going to die from this is scary, this is bad, oh my God, this is even worse. And, it's like, who in their right mind would want to be a chemist today in 2018? We've got all this nasty information about all the bad things that chemistry is doing. And then when we try to communicate, to the general public, it's like the game Whack-A-Mole. You know the game Whack-A-Mole? What is the mascot of the American Chemical Society? It's a mole. Okay, we're playing Whack-A-Mole. We hear about brominated inflammatories, whack. We hear about bisphenol A, whack. We hear about phthalates, whack. We hear about nanoparticles, whack. We hear about ocean plastics, whack, and we're out of breath. We're trying to wrap our heads around one issue, and by the time we start thinking about it, another issue comes, and then that issue starts going, and we're wondering, do we have this right? Is this really scary, or is it a bunch of hype? But we don't have the time, we don't have the patience, we don't have the luxury, we don't have the knowledge to actually truly assess what's going on. It's just happening too fast, and it's just strange. Then, when it comes to companies selling us chemistry, look at these beauties. All right, if you buy any of these buildings, you get a class action lawsuit. You should demand your money back. Okay, this product is chemical free. This product, chemical free. This product, chemical free. So what are you buying, an idea? Do you have packaged ideas when that substance that seems to appear to be a substance of matter appears on your body or whatever you're doing, but they're saying it's chemical free? Well, what exactly is that? And this actually really angers me because, of course, the people writing these ads understand that there is no such thing as chemical free, and they're playing on people's, I won't say ignorance, but fear of the chemical enterprises. And I don't think that this helps anybody. In fact, I would myself personally never buy a product from a company that markets any line of their product as being chemical free. It's just being disingenuous and wrong. But what we can't do With all of this inundated bad news, what's not an option is to despair. You know, people don't get up out of their seat to do anything out of it. Imagine if Reverend Dr. Martin Luther King got up and said, I have a nightmare. Okay, rich people would have written checks. People write checks out of scary stuff. But no one gets up and rolls up their sleeves and says, I'm going to dedicate my time and effort to something that is just all about scary sadness. You know, if we're really going to make a change, we've got to understand that there's got to be a positive path forward. So I feel we haven't really, in this place of chemicals, policy, and sustainability, we've not really been asking the right questions. Instead of asking, you know, all of the biggest, most fundamental question that we should be asking is, why would a chemist make a hazardous material in the first place? Let's assume no one wants to make that. Let's assume there are red dyes in commerce that cause cancer. Let's assume that there are plasticizers that cause birth defects. Let's assume that there are things that cause endocrine disruption. No one wants to do it. So how did that happen? So instead of asking, how do we make molecules? Maybe we got to be asking ourselves, how do we make chemists? Maybe there's something there that we've kind of missed. Now, I'm not a historian. I'm not a sociologist. I can't quote the history of science. I am a chemist. So maybe something in the road that I took to become a chemist is useful. So let's just look at what happened in my world becoming a chemist, okay? So anyone who knows accents might hear in my voice that I'm from the city of Quincy. It's a very distinct South Boston accent that I have. Great city of Quincy. 2 presidents from the city of Quincy. In my opinion, one of the most famous, most wonderful chemists that ever lived, Robert Burns Woodward, is from the city of Quincy. Would have gotten 3 Nobel Prizes had he lived long enough. But the city of Quincy, I come from this huge Sicilian and German family. I had 42 first cousins growing up within a 1-mile radius. And we were carpenters, plumbers, electricians. We weren't into this thing called college, okay? I didn't one of these kids in the 2nd grade that had beakers and flasks and dreamed of being a chemist. I had no idea what chemistry was. In my high school, when I had English on the 2nd floor, I thought that was higher ed. I didn't know what this was. And one day, because my friends seemed to be doing this, I came home and I announced to my parents I was going to college. My mother cried, my father got mad. I made a deal with them that I would work full-time in the construction industry and pay my own tuition, and I went to the University of Massachusetts, Boston. At the time, $200, actually $195 a semester. Okay, and so I went there, but what horrified my family was not the fact I was going to college, but what I went to college for. You see, I went to college as a music major. But wait a minute, the name of the band that I played in was The Elements. Okay, this had nothing to do with carbon, hydrogen, nitrogen, okay, nothing to do with that, the Rubik's Cube, a ball, or something like that, okay, it was the late 70s, okay, give us a break, those were our elements. And we were okay. When I say okay, we were playing in the best, worst dives in Boston 3 nights a week. We had an agent, you know, things were going good. We actually had a recording contract. We were recording in the same studio as Jay Giles. They were a grown-up band. We were idiots. But we even one Wednesday evening at 2:30 in the morning, if you listened to WFNX, you heard one of us say, so we were on the radio. So things seemed to be going okay when disaster hit. The drummer, my close friend, got leukemia, and over 6 months, he passed away. And all of a sudden, my life is very different. It's all about music. But at UMass, even a music major has to take a math class, has to take a foreign language, has to take a science. Oh my God, I had to take a science class. Well, I kind of liked biology, mitosis, meiosis, genetics. That seemed kind of cool. I kind of like physics, astronomy, subatomic particles. That seemed kind of cool. Oh, should I take biology? Should I take physics? Should I take biology? In a moment of inspiration, I added them up, divided by 2, and I took chemistry, not because of any interest, but because of my indecision of biology and physics. And I took chemistry to fulfill my science requirement. And I'm in my teaching lab, doing the chemistry lab, when this Professor Jean-Pierre Anselme comes in one day, looks at me, music major, walks on by, and asks the kid next to me, would you like to do research? I overheard the conversation. I got some time on my hands at the moment because of what's going on in my life with music. And I said, can I come? And I followed them into the research lab. And when I got into the research lab, everything changed. For all my life, because I was marginally okay at music, I was an artist. And in the world, there were two types of people. There were artists and there were scientists. And they were just very different things. And that's just who I was. But when I found out by seeing research in the lab that chemists and scientists imagined things, they created things, they designed things, all of a sudden I had this image of ramming my brain full of electrodes and composing a piece of music on a piano keyboard or designing a molecule. And I said, I bet you the same neurological activity is happening here. That bringing something new into existence doesn't know the word art, doesn't know the word science, it's just human. And once I figured that out, I fell in love with chemistry. Next thing you know, I'm spending 50, 60 hours a week in the chemistry lab. I published 5 papers in peer-reviewed journals. I spoke at the National Academy of Sciences in Washington. I get all these. In fact, I made the cover of Celebrity magazine with Boy George. Now, if that's not a claim to fame. One day the phone rings in my house, and it's this guy with an awesome voice, John Warner. We consider you one of Boston's best and brightest college graduates. We want to do a story on you. I said, no, thank you. I hung up the phone. A couple minutes later, the phone rings again. No, really? And I go, really? I hung up the phone. The next day, I go into school. Now, I'm not as snappy dressed back then as I am now. I'm not shaven. I'm working in construction afterwards. I'm working in my lab. And the chancellor of the university comes and bangs on the door, and he says, you will go get your picture taken. So they grab me, kicking and screaming. With all these snappy dressed people, there I am, hating life, as they do this story on this kid who has made over 100 molecules that have never existed in the world, assembling atoms in unique geometry that God never intended. And I'm reading this thing and I'm saying, I'm a chemist. How did that happen? Well, through flotsam and jetsam, the next thing you know, I find myself at Princeton University working with this amazing guy, Ted Taylor, working on synthetic strategies to anti-cancer drug that ultimately became Alimta, sold by the Eli Lilly company. Now, hundreds of people worked on this. I played a very, very tiny role, but I'm actually the witness on the invention disclosure of this molecule. If you go to Princeton, they have a 7-story chemistry building now built entirely on the proceeds of this building. Princeton's pretty psyched about this. I just had a beautiful time working with so many amazing people, and this guy here, it's interesting the way the world works. I lost my mom in the early 2000s to cancer. At the time, she was receiving a form of the drug that we had designed at Princeton 15 years earlier. So this relationship between science and society has really been kind of interesting. Well, this is my dad on the day I graduated at Princeton, my commencement. This is my lab. I never dared tell him I was a graduate student. He would have killed me. I told him I was an apprentice. And so he was okay with that. So he came down, and in the lab, he's kind of looking at a telephone. It was a different model than this. But one day I'm working in my lab, and the phone rings. And it's a senior corporate officer from the Polaroid Corporation, the instant photography company. This guy's kind of weirding me out. He goes, oh, John, I've been following your career. I remember you when you were on Celebrity magazine. I remember you at the National Academy. And I go, God, this guy's a stalker. He goes, let's have lunch. I told 6 people where I was going, and when I'd come back, I'd go and have lunch. And at lunch, he offers me the job to head exploratory research at Polaroid. Dude, I'm 25 years old. I've got 2 academic appointments to be a medicinal chemist in academia. He told me how much he's going to pay me. I said, when do I start? And all of a sudden, I'm an industrial chemist. Who knew? And I was blessed. Edwin Land, one of the nation's greatest inventors. It's like, oh my God, what an opportunity to work at Polaroid. Edwin Land, one of my heroes. He got the Perkin Medal in 1974. Oh my God. And they gave it to me, so how good can it really be? But I was blessed that I had a great group of people and just got to crank out patent after patent in holography and medical diagnostics and film forming and just doing all kinds of crazy little things and just had a blast. And got a lot of things into a bunch of different products. One of the things, though, is what would? a medicinal chemist do at a place like Polaroid? Well, I was very introspective about the chemical sciences. You know, we do amazing things in chemistry, right? The pharmaceuticals, the ag agents, the electronics, all the different things that we make are so cool. But the way we manufacture everything, everything's at high temperature, everything's at high pressure, everything uses harsh reagents, and yet, as a medicinal chemist looking at physiological processes, everything we do in natural systems, in the birds and the bees and the bunnies and the bugs, all of those things happen, you know, the molecular diversity and complexity outperforms humans, hands down. But everything happens at room temperature. Everything happens at ambient pressure. Everything happens in water. What gives? And what I realized is that in us humans, everything we do is what we call reactive collisions. We dissolve molecules into solvents, they bang into each other. What we learn in chemistry is that the shapes of the molecules and the atomic orbitals impose precise geometries, and only certain trajectories of collisions work. So when we heat things up and put things under high pressure, all that's happening is things are banging into each other more often so that what we want to have happen happens. My epiphany was that in nature, there is never a reactive collision. Always in nature, in a semi-viscous state, the molecules use those very same molecular orbitals and atomic orbitals that govern reactivity to govern orientation. And they actually snuggle up to each other first, then they react. And so I said, oh, if I can do that, and I can, instead of doing methyl, ethyl, propyl, butyl, futyl derivatives of molecules, I can take multimolecular systems and cause them to orient. Maybe I can control their properties. And I called it non-covalent derivatization. All right? And so if you wanted me to talk about this for about 30, 40, 50 hours, I could. All right, I really get into this. The license plate of my car is NCD, okay? I really get into this. But I will spare you all of the nuances of this fabulous and wonderful thing, other than to say one of the inventions the photographic industry actually started calling Warner complexes. And it was a way of controlling the dissolution kinetics of multimolecular systems in which during the formulation process, you coalesced the two materials and could precisely govern the kinetics of dissolution with these multimolecular systems. Right? So anyways, in the United States, if you have an invention that you're going to manufacture, you got to get EPA approval. This is what TSCA is all about. You get what's called a low volume exemption. You get what's called a pre-manufacturing notification. Before internet, before the email of things and stuff, and so we fill up bankers' boxes, tape it up, mail it down to Washington, and we waited, and we waited, and we waited. And they ultimately rejected the application. Nothing to do with toxicity, nothing to do with environmental impact. They said, small particles, are you crazy? Molecular complexes, are you high? They had no idea what I was talking about. You know, they never heard of non-covalent derivatization. So Polaroid stuck me on an airplane and sent me to Washington. It was the first or second time in my life I'd been on an airplane. I'm holding my briefcase of overhead transparencies. And I'm standing at the foot of the Office of Pollution Prevention and Toxics to meet this guy named Paul and ask this. Wait a minute. I know this guy. Remember the kid that I followed into the research lab when I was a music major? It was him. I've known him since he was 11 years old. We've gone to UMass together. In fact, I was playing in a jazz band with his older brother. There's his older brother. There's me. My older brother with awesome hair. And this guy playing the guitar, if you've ever been to Las Vegas, the dude who plays Rod Stewart in Legends of Rock, it has nothing to do with this talk, just thought that was cool. But anyways, I could say to Paul, dude, Polaroid has been manufacturing this thing for years with all these solvents and energy and everything. Here we have this replacement technology that's aqueous, non-toxic, room temperature, and you're giving us a hard time because it's different. Isn't anything better for the environment, by definition, going to be different? Isn't there a conundrum here? So here I am, a Polaroid employee, down at the EPA, talking about this. And at exactly the same time, things are going well at Polaroid. My career is doing really well. I've got all these patents. Everybody's patting me on the head. When disaster hits, in yet a worse way imaginable, I lose my 2-year-old son, John, to a birth defect. My 2-year-old son, John, dies of a disease called biliary atresia, where his liver is completely detached from his intestines. They give him emergency surgery at birth, and at 2 years old, we lost him. And lying in bed the night of his funeral, I'm staring at the ceiling, and I'm asking myself, wonder if something I touched caused my son's birth defect. Wonder if something, heaven forbid, that I got an award for or something caused his disease and ultimately. So I'm racking my brains, and the fact that I didn't know the answer didn't bother me as much as I didn't know how to answer the question. Nothing. I'm familiar with books like this, Our Stolen Future, that talks about the impact on chemistry. At this point, I'm one of the most prolific synthetic organic chemists my age on the planet, synthesizing thousands of new molecules, not resyntheses, thousands, hundreds of awards and patents, all the stuff here, and I realized I have no idea what makes a molecule toxic. So I start looking. All right, there's all kinds of information about elevated types of tumors and cancer, and elevated breast cancer, mortality among cancer, report after report after report. How was it possible that 4 years of undergraduate, 4 years of graduate school, I never had a seminar, I never had a conversation, I never had a discussion, I never had anything that talked about how do you think about a molecule and how it might be toxic to human health and the environment? Yeah, I learned how to label the waste. Yeah, I learned all the things from a litigation perspective to protect the university. But at an intellectual basis, there was nothing in my education that trained me that. So I started looking. In the United States, every year, we graduate 15,000 undergraduates in chemistry, 3,000 masters, and 3,000 doctoral degrees. In 2004, more women started becoming chemists than men. What could be more important to the field of chemistry than an understanding of reproductive hazards, of carcinogenicity, of toxicity, and having to be, and yet, not one university in the world requires a chemist to show any expertise in understanding what makes a molecule toxic, what makes a molecule hazardous. Why do we have red dyes that cause cancer? Why do we have plasticizers that cause birth defects? Why do we have these things? This isn't some epic battle of good and evil. This is an industry saying, wow, we're going to make money off of a nasty. For some bizarre reason, the field of chemistry has evolved not to see this as self-definitional. To not see this as who we are. This isn't an evil, bad thing. It's just a weird historical anomaly. All right? And so Paul and I realized for this to work, we needed not to have a philosophy, not to have a policy. We needed a science. We needed to bring people together to share in how we can go about doing this. We needed journals. We needed textbooks. We needed classes. We needed conferences. We needed workshops. And so we wrote this book. It's actually 20 years ago. In 1998 it came out. We started writing it several years earlier. I got to tell you, had I thought anyone was ever going to read this book, we would have written a better book. All right? But it's like you turn the pages and you wait. And you go, okay, I'm waiting for something or shaking. I'm waiting for something. Yep, nope, that makes sense. Yep, that makes sense. Yeah. It's just complete common sense. Anyone could have written this book. There is nothing magical or shaking about it. It's just sometimes the most common sense things people just take for granted, and so that's it. And I feel like, you know, Forrest Gump. This thing has been translated into over 15 languages now. Okay, and oh my God, I've been everywhere. I'm meeting politicians. I'm meeting presidents. I'm meeting princes, and I'm meeting that guy. And just. Little old silly old me, been to over 50 countries, cutting ribbons and giving talks for something that anyone could have done at any time. It's just a common sense thing that, gee whiz, before you make a molecule, that's when you should probably anticipate what it has potential to do, not after. All right, and so, but what I think is the most important component is the 12 principles, because that reduces it not to a philosophy, but to a set of principles. Now, it's interesting, when you think of sustainability, you say, well, what is sustainability? And everyone has a different definition. When you think of clean chemistry or clean tech and all these other words, they're all kind of nebulous. Green chemistry, there is no confusion. There is a definition, there are 12 principles, and any misunderstanding is through intent, not through the actual reality of it. And so I've just been blessed that almost immediately, almost every company that I'm aware of embraced green chemistry. Dow started a green chemistry program. DuPont started green chemistry. 3M put the 12 principles as part of their stage gate process. Pfizer, Lilly, so now within a few years, it became a commonplace thing in industry. All right? Because my definition of green chemistry is, yes, the technology must have some benefit to human health and the environment. But if it's sitting on the shelf with people celebrating it just by talking about it, and it's not successful in the marketplace, it's actually not solving any problem. So for it to solve a problem, it's actually got to work better than any other technology. It's got to cost better than any other technology. So the philosophy is that if we are dependent on a regulatory system that forces people to use inferior products that are too expensive, which I would argue sometimes we must do to protect human health and the environment, but if we're overly dependent on that system, change of an election, change of a social policy in Washington, hypothetically, all that could come down like a house of cards. So true sustainability is if the chemist and the engineer gets their butt back in the lab and invent something that works better, costs better, and oh, by the way, here's the sustainability narrative if you want it. Then and only then do you have green chemistry. Now, the chemical enterprises have been in business for well over 200 years. We're not going to snap our fingers and do this overnight. This is going to take decades and decades, perhaps centuries, to figure all this out. So we all got job security here, all right, because there's a lot to do. But we got to get moving in that direction, all right? Because if you accept that definition, that essentially, if it works better, costs better, and oh, by the way, there's some sustainability, there's no barrier. That doesn't exist for any other breakthrough technology. People were selling vacuum tubes years after the transistor was invented. No technology in history lied down on the floor and said, take me, I'm yours. We have this thing to push back. And so yes, there's always going to be pushback in the market, but there's no added pushback in sustainability if the performance and the cost is met. All right, so the only barrier, in my opinion, that we need to be focusing on is the invention in the first place. Do we have a workforce that is capable of inventing these things? All right, and so I realize this isn't an industrial issue, this is an academic issue, so I quit Polaroid, and I went to UMass, chair of the chemistry department, director of biochemistry, chair of plastics, full professor of plastics engineering, all these different things, and we started the world's first PhD program in green chemistry. Everything that's in a normal chemistry program, but we added a one-semester class in mechanistic toxicology. We added a one-semester class in law and policy. We added a one-semester class in environmental fate and transport, just so that these students had everything that's in a normal program, but added to it these other things. You know what? Over the next 11 years, over 120 students at different levels passed through this program. The average time it took one of these students to get a job in industry, 2 days. The longest any student spent looking for a job from this program was 2 weeks because she turned down the first couple job offers. I've been out of academia for over a decade. I still get phone calls from companies, John, you got anyone coming out? Because they actually know how to solve problems, but they got a clue about the commercial realities of the environment and human health. So the way I look at it, of all the products and processes available to our society today, maybe 10% escape somebody's scrutiny. 90% of them have somebody that's got an issue. Now, sometimes these issues are very serious, and sometimes these issues not so much, but 90% of them need something done. If you do what's called an alternatives assessment, and you search in the supply chain for something better, maybe 25% of the time you'll get lucky and find something. But right now in 2018, I would argue 65% at a minimum still need to be invented. Now you can look at this in despair, or you could say, what better time in human history to be a chemist, to be a chemical engineer, to be in the business of inventing stuff? The world needs us. Why is it that some 8th grader dreaming of saving the world, whatever that means, eyes as big as silver dollars, is chemistry on the top of their list of where they're going to go when they do this? Probably not. Who's going to invent the new technologies? What are we doing wrong that chemistry is the problem when in fact the reality is chemistry is the only solution? We need to invent a sustainable future. We need to make sure that people understand this, especially the K-12 community, because that's where our hope is. All right? And so green chemistry isn't the birth of ethics. Chemists have always cared about this. Okay? When I was a music major, I actually asked a chemistry professor, is chemistry dangerous? If I choose to go into chemistry, will I put myself and my future family at risk? The clairvoyance of that question. You know what his answer was? In a very loud and up like this, if you're asking yourself that question, you should probably get another major. Okay, no, I never asked the question again for quite a while. It's not because he's evil, it's not because he's bad, it's because chemistry has to be toxic. By definition, chemistry is scary dangerous, but it's okay because we wear gloves to protect our skin. We wear masks to protect our lungs. We wear goggles to protect our eyes. We install scrubbers and filters and smokestacks. The air, the land, and the sea, we got it covered. My first slide of all those disasters, if you ask the people the day before, you got it okay? No, yeah, of course we got it okay. We've got all this stuff. Stuff happens. And so the point is that historically we have focused very admirably, standing on the shoulders of giants, mitigating exposure. And every time someone talks about mitigating exposure, it by definition comes at an added cost. How are we going to engineer protection by controlling exposure? If green chemistry is a revolution, it's saying, but wait, if the chemist looks at the structure of the molecule and mitigates the intrinsic hazard to lessen the burden on the exposure control, not only is it cost effective, but if a big tanker truck screaming through the town tips over, instead of getting body bags, you get a broom. Now this is a utopian vision, as I've said, that is going to take probably a century to even start approaching, hopefully a lot faster. But it's something that's worth us all working towards. Because again, as I said, industry immediately understands. If you got a nasty and you've got a safe, the cost of the storage, the treatment, the disposal, the regulatory liability, work health and safety, on and on and on and on. It just makes so much more sense and much more cost effective to have something that is managing that risk. I think this last one is super important. Okay, I think it's super important because employers have figured this out. It was really kind of a cool moment. One of my students, the National Academy of Sciences, got an award. She designed these ways of lowering the temperature of processing semiconductors, titanium dioxide semiconductors. She got an award from the EPA, so she gives this presentation. And at the end of the presentation, everyone politely claps. There's about 300-400 people there. And some guy gets up. And he goes, excuse me, ma'am, but aren't you concerned that having green chemistry associated with you is going to limit your career opportunities? And she looks at him and she goes, dude, why would I want to work for a company that didn't want me to do green chemistry? And he, in a knowing way, you silly person, and sat down. At which point, about 180 graduate students stood up and gave a standing ovation. If there's ever a book or a movie, that's the end, okay? Because that's when I looked there and I said, yeah. This isn't going to stop, okay? And so, but it's our job to enable it. The desire is there. The enablement isn't. What I did is I went back to Abraham Lincoln's time and I tallied all the environmental regulations imposed by the U.S. federal government. Not a whole heck of a lot happened. In 1962, Rachel Carson publishes Silent Spring, the year that I was born, and all of a sudden, you see something happen. These are all dots, pieces of federal legislation saying if you're working with this, that, or the other thing, you gotta make sure it's not getting into the land, the air, and the sea. I'm just a simple chemist. I'm not a mathematician or a statistician, but if I look at this long enough, I detect a trend. All right. Industry recognizes that one of the single biggest impediments to success in the commercial marketplace is understanding the existing regulation and the future regulations. All right. Many multinational chemical companies have $1 billion plus R&D budget a year. Those companies that have $1 billion plus R&D budget oftentimes have an equivalent $1 billion environmental compliance budget. They spend the same amount of money inventing their future as they do making sure they're compliant with all of these things. So the CEO says, from now on, this is all a lot of waste of money. We want all my scientists to only invent non-toxic, environmentally benign things. It'll make us so much more profitable. Oh yeah, but not one of those scientists have had a class in mechanistic toxicology. Not one of those scientists have had a class in... So the desire, the need, the imperative has been there for a while. It's the supply of that skill set that is missing. Big financial analysis firms have figured this out. They claim that green chemistry would be a $200 billion industry by 2020. It already is. All right, and so that's why, you know, you name the company. If you Google the name of a company in green chemistry, you'll find a web page in their sustainability organization with the 12 principles saying we do this, we do that. There's no trouble convincing industry about this. And you know, my dad was an electrician. I grew up surrounded by toolboxes. My poor mother, silverware in the kitchen was in a toolbox. I tend to think of the world in such a way. The chemical enterprises has a toolbox. All right, and each draw has a different type of chemical transformation: carbon bond forming reactions, oxidations, reductions. If we can design a molecule that doesn't violate some law, we can probably make it. But if we imagine a green chemistry toolbox of those same transformations, I told you it's like 10%. It's 90% empty. I am convinced that an individual, a company, a developing country will open the green chemistry toolbox first. It just makes smart sense. But statistically, the odds are ain't going to be nothing there and inside that drawer. So what do? The way our world and our economy is based, they got to make quarterly deliveries. You can't schedule an invention. You can't say next Tuesday at 2:30 we'll invent the solution. Yeah, that's not the way invention works. So they close the drawer. They figure what they're going to cost for the gloves, for the masks, for the lawyers. They open up the traditional and they do business as usual. And so our job is to get things in that toolbox. All right? And that's so important to me. And that's why on an invitation to come to MSU, of course I'm going to jump into a plane and come talk, because this is where it's going to happen. All right? So I have a great time in academia. Actually, in 2004, I was called the country's #1 science professor. I spent a half an hour in the Oval Office with President Bush. I don't know which one of us looks more shocked about that. And so what do? I quit. I left academia. Here I go again. I was doing good at Polaroid. Now I'm doing good in academia, but I quit. But this is why I had to quit. When Canada banned Nalgene, the big news story. Okay, Canada bans Nalgene because of bisphenol A. Now, because I'm a peppy guy that has nice quirky quotes, every science writer, whenever there's a sad story, they call me up and ask for some quote. Cheer us up, John, this is terrible. And so I'm driving in my car, my phone rings, and they say, tell us something about BPA and Nalgene. So I dutifully pull over the side of the road, and I go into a parking lot of a grocery store. And while I'm talking, a pregnant woman comes out of the grocery store, and she's stumbling with her bags, she's stumbling with her keys, she puts her cash register in her mouth, and and like a neuron just went pop. And I'm looking at it, and I go, you know what drives me crazy? We're spending all this time talking about bisphenol A in plastic bags. Femtogram quantities of bisphenol have to be depolymerized from a polycarbonate polymer, but yet in a thermal cash register receipt, you've got free milligram quantities of bisphenol A holding onto a cash register for 30 seconds. You will completely exceed a lifetime out of drinking out of plastic bottles. And they go, calm down, we're talking about plastic bottles. And so they wrote their paper, but they mentioned John Warner Reveals. bisphenol A. I don't reveal anything. It's I just next thing you know, thousands of websites. John Warner reveals bisphenol A in cash register receipts. I'm on Tom Ashbrook. John Warner reveals bisphenol A in cash register. In this world-class journal, on the same page as a cat pushing a shopping carriage, John Warner reveals it. I'm holding it and I go, it's time for a change, man. You know, my whole life I've been trying to invent technologies to solve problems that no one cares. The one time by accident I identify a problem, and I get more notoriety from identifying the problem than solving it. And I said, I can't do that. That's not the way to go. So I quit UMass, and I met this guy, Jim Babcock, and we started the Warner Babcock Institute for Green Chemistry. And again, I pinch myself every day what a lucky, amazing thing this is. This guy is just so cool in the way that he sees what the opportunity was. So the idea was, pretty successful in my academic career. I'm not starting from my garage. I want a 42,000 square foot building with every piece of equipment necessary to synthesize small molecules, to synthesize polymers, to extrude plastics, to coat things, to fabricate devices, to test the devices. Literally every piece of equipment I've ever seen or touched or imagined in my life under one roof, hired 25 of the most brilliant scientists that I could, and we just invent stuff. We don't publish papers in journals. We don't speak at technical conferences. We focus entirely on invention. And so the way the Warner Babcock Institute works is most of our business is contract invention, not contract research, contract invention, where the multinationals or the small companies pay us to invent. We invent, file the patents, and then make a deal on how we'll share in the profits. We've got some government grants. We've got a NASA, DARPA, Department of Energy. All these have gone into phase 2, and so we're pretty excited with desalination projects, sensors for spacecraft and things like that. We invent some technologies to license to other companies, but we've also spun out a handful of companies. The sponsor of this event and working with the great people in the pavement industry around here, Collaborative Aggregates, wait for it, okay, and is our material science company, and then Collaborative Medicinal Development is our pharmaceutical company that has little spin-outs underneath that. And so to kind of give you a sense of what it means, green chemistry from an invention perspective. In the pharmaceuticals, we were all over the place. We got an ALS drug in clinical trials, an Alzheimer's drug we're trying to get into clinical trials, an oncology drug in clinical trials, a diabetes drug, and so we're working on it. But it's interesting, the same people who are pouring the beakers and flasks, synthesizing these pharmaceuticals, are standing by people who are working with asphalt products. So for people who aren't in the asphalt industry, there's 1 billion miles of asphalt in the United States, and every year about 10% gets repaved. Because the sun and the air oxidize the surface of the asphalt, making it brittle, it gets dug up, put in a landfill, and some amount of it can be ground up and repaved, but not a whole heck of a lot. And so I'm looking at that and I'm dreaming, oh, if I could invent the street Zamboni. All right, come that way. I'm from Boston, okay? You gotta forgive me for this, but the idea of having it and just dig up, process it, and have no inputs or outputs other than an additive. The energy isn't quite right yet, but we did come up with an additive, and so a couple days before Thanksgiving, a few years ago, in a bold move, I dug up my driveway. My wife was upset because it's like 2 days before Thanksgiving. It was a perfectly good driveway. We dig it up. It's 17 degrees Fahrenheit. The guy's in the dump truck, so we go to the place. We pour the additive in and process it, and the guys are laughing at me. They say, "John, you idiot. We've never paved at this temperature. You've got a ridiculous amount of recycled content. We're going to open up the truck. A big hockey puck's going to come on your front lawn. We're going to drive away." I said, "Oh, okay." And they open it up, and it comes out like sand. They scream like school children, jump on their bulldozers, and here it is 3 years later, beautiful. And We've been having a blast. We started a company called Collaborative Aggregates. The product, I wanted them to call it entropy mix. And they said, oh, could never call it entropy mix. I said, how about delta S? They go, oh, we like that. Don't tell them. All right. And so, and again, I've been blessed to learn so much about the pavement industry and coming and visiting in different groups about this thing. So this is an example. Right? Now, you might say that's kind of weird. Here I am. I'm wearing a hard hat and boots, holding a shovel, digging in a pile of asphalt. And my cell phone goes off, and it's clinicians in Finland talking to me about the results of the Alzheimer's drug. Now, wait a minute. Asphalt, neuroscience, that doesn't quite go. But wait a minute. My mechanism for Alzheimer's is there's a protein in the brain that wraps around an inorganic particle and it aggregates. And so the molecule that we invented slips into the interface and controls the way it aggregates. What is asphalt? Organic polymer wrapped around a particle. What is delta S? A small molecule that slips into the interface. It's the exact same thing. We in science, we love to define ourselves. I'm a medicinal chemist, I'm a cosmetic scientist, I'm in construction. A molecule doesn't know what industry it's in. If you just look at molecular structure and molecular behavior, you kind of can play all over the place. And so while we're solving the asphalt problem, we're learning about Alzheimer's. While we're working on Alzheimer's, we're solving problems in asphalt. At a molecular level, they all just kind of go together. And it's these barriers we give to ourselves, this desperate need to put ourselves in little boxes that prevents us to being as innovative as we need to be. We have, it's interesting, I had this form of psoriasis that had a phototherapy cure where I had UV light and had to go to the hospital 3 days a week, 6 months, and I'm cured. This is back in the 80s. All right, but I'm thinking, what's going on here? And I learned that the UV light in psoriasis is a miscue of cells over-proliferating. And so the UV light shines on thymine and DNA very efficiently. So I said, an efficient reaction from biology. So I rushed to my lab and I started making polymers based on thymine. So I made either styrenes or water-soluble polymers or biopolymers, and I found that the thymine self-assembles, molecularly snuggles up, and when you put a tiny bit of light, it undergoes a chemical reaction. Next thing you know, I have a hair curling technology based on this. You know those carnival lights that you click? You take the solution, you wrap it in the hair, you click it, and the hair stays curly. We've got fabric, wrinkle resistant and holding plates in this technology. Now, so usually people use formaldehyde for this kind of technology. Well, what else uses formaldehyde? Wood. So wood is the #1 construction material is OSB lumber in North America. You've heard about in Hurricane Katrina, the off-gassing. You heard about lumber liquidators. Well, here's a technology that's using something else. Now, we didn't use exactly the thymine-based technology, but something that's not too far off. And we came up with a way of doing wood composite technology. We went up to Alberta, Canada recently, did a 70-ton pilot-scale run of OSB lumber. It outperforms industry standard in performance, about par and cost, not a drop of formaldehyde, not a drop of MDI. Pretty excited about that. Here's a weird story. One day I was thinking about bugs and how when the exoskeleton grows, the exoskeleton can't grow, so the bug sheds it. And over the course of a couple hours, turns hard and black. I'm going, Other things that people want to do, white from black, they help people color their hair. So, wait a minute, this is the leading men's product for coloring hair. The key ingredient, lead tetraacetate. Lead tetraacetate. You can't sell a house in the United States with lead paint, but you can pour it on your head. And so I look into this, and it's a tyrosinase cascade that controls this sclerotization process. So I mimic it. I don't grind up dead bugs. I mimic this biochemistry, put it in a beaker. I bought a bunch of gray hair. I put it in, and it worked. But some was dark, some was light. It wasn't all the same color. I called the vendor, and they said, oh, John, that's not one person's hair. It's a bunch of people's hair. Oh. So I'm the grayest person in Warner Babcock, I jump in here, hit me. And my hair goes back to the color it was 30 years ago. Someone with black hair that's gone gray goes black. Someone with brown, it goes. What I realized is that I discovered a way to return the human pigment. This doesn't color your hair. This doesn't paint your hair. If you invented a time machine and took a snippet before and after, it is the exact human pigment. So strand by strand, it is your real color hair. And so in the same way that your finger has a fingerprint, your hair has a hairprint. So Paul Hawkins, famous sustainability guy, licensed it, and for the last 3 years, online, myhairprint.com, you can get hairprint in for $39.99. If you act right now, they'll throw in a knife. Okay, and so this is something that's non-toxic, environmentally benign, it's permanent, it won't wash out. It grows out. It'd be a lousy product if you sold it only once, but it's really kind of exciting. A couple years ago, I found myself on the center stage of the United Nations General Assembly. There's my big head up on the screen. Oh my God, what are they doing there? Whale Wars is a show in which they're protecting from environmental pollution and illegal fisher people doing illegal bad things. Well, they're in La Rochelle, France, and they just got 75 tons of an illegal fishing net. And so they have this stuff, and they say, oh, they send it to me. All right, and I got 2 weeks. And so what we do is we have to separate the nylon from the polypropylene, have to pull out the heavy metal, we have to pull out the pigment. They want it extruded to a very specific dimension. We don't have the right extruder. We find a plan on the internet, we build the extruder overnight, and then yards of it, we send it to Adidas in Germany, and standing beside me, a guy on the board of directors of Adidas holding up the 2016 model running shoe made out of ocean plastics. We did that at WPI in 2 weeks. Orange recycling, when EPA declared limonene a skin irritant, many products stopped using it. What are we going to do with all this orange oil? So again, I can't explain why some of these things occur to me. It's kind of frightening. But I said, if I hydrolyze limonene to a 50% mixture, probe sonicate it in water, I bet you I can tune the density so that I can fully recover lithium cobalt from the battery. And we have 2 pilot plant things going on now where we recover lithium cobalt from lithium batteries, not using kerosene, not using flammable toxic materials, but using water and orange oil as the flotation medium. We have a water harvesting technology where this polymer, when the light is on, it absorbs water. When the light is off, it repels water. So imagine a rowboat on the ocean. This is an oversimplification. When the sun comes up, water absorbs on the underside of the umbrella. When the sun goes down, it rains pure water in the rowboat. We have this technology that either works slowly in a diurnal cycle of the Earth or in millisecond cycle in the shadow of a windmill to capture and release water. We have a bisphenol A-free can lining technology that a Korean company has licensed and is going forward with. We have, of course, because it started it all, a BPA-free thermal cash register receipt technology. But the point is, I would argue the Warner Babcock Institute is no more smart, no more creative than any other group of people. Okay, we're not successful because of some magic. Okay, what I feel it is that we're successful not in spite of green chemistry, but because of it. All right, if you take any group of scientists and you give them a restriction, they're going to squawk, they're going to cry. But wait a minute. Everyone learns from the same classes, the same textbook. Everyone's doing everything the same thing. Anything that makes you do something different. If I said, from now on, you can never use a molecule that starts with the letter D. Well, that's kind of silly, but you know what? Those people will all of a sudden do things different than everyone else. Now, not using the letter D seems kind of arbitrary and silly. What about saying, let's focus on human health and the environment as a design feature? It doesn't slow you down. I don't feel slowed down. What I've just described to you is just in the last 4 years with under $6 million of investment. I don't feel that this slows me down, but I don't think that we're anything special. I think that it's just when you free your mind to see that these constraints in green chemistry project you forward in creativity, it's where it's at. But what I'm really, really proud of is at the same time, within the Warner Babcock Institute, you'll see in the corner, Beyond Benign. Beyond Benign is a nonprofit that is run by Amy Cannon, my wife. When I was a professor at UMass, I had a very large program. I never had any grants or funding for this, but I had an inviolable rule. Anyone doing research in my lab had to twice a month go to a 3rd grade class, a 7th grade class, and explain their research. All right, and everyone loved it. I didn't have any funding. Over the years, over 100 school systems became dependent on this program. When I quit to start one at Babcock, because I had no grants, I was just doing it because I thought it was the right thing to do, no one was going to pick it up. So Amy, also a professor at UMass the same time, quit the same day and started Beyond Benign to continue the K through 12 and university education program as a nonprofit. And the thing that I'm most proud of, there's a lot of K through 12, but I'm running out of time, so I'm not going to talk about that. The thing I am most proud of, and I think is the most important thing I personally do, is what I call the Green Chemistry Commitment, where we're looking at university chemistry programs and associated programs, and we're saying, we've got to find a way to get this into the curriculum. We have to find a way to get this in so that someday no chemist graduates and goes to industry or to academia not having this fundamental stuff. And while it's hard, because it takes a special group of chemists to be willing to roll up their sleeves and say, let's look at the chemical enterprises and change it. We've been really, really lucky that there's nearly 50 signers already. And as of last week, if you make a little space here, Michigan State University signed the commitment, and so I am so proud to be here at Michigan State, where you guys are leaders of the field of green chemistry. You guys are the epicenter of where things are happening, and I thank you so very much for doing that, and I thank you for listening to me babble.
Day that thermodynamics, which are things we can't get around, demand. I think a very useful, low-cost fertilizer. How do you address people who, say, is this a limitation, or is this a, how do we get around, or can we get around these kind of barriers that you can't go through?
Right.
So there's a lot of them.
Right, and so I would submit that every breakthrough technology had people saying it was impossible because of thermodynamics and genetics and stuff like that. So that to me is not in itself a reason to not try. But again, we have to continue with exposure control. We have to continue to protect human health. This isn't like, let's just drop everything and do something else. And there are some things that are going to be around for multi-generations and perhaps forever. All right, and so this isn't saying that, if you came into my lab, every toxic nasty that you can imagine, this is collaborative aggregates. I would never be so presumptuous as to show up someplace and hand out my books. I'm a little embarrassed by this, okay, but thank you. But there's every nasty material, that the 12 principles of green chemistry, no human being can tackle a problem and address every 12 principle. The way science works is someone might reduce the energy, someone might make it a little less carcinogenic, someone may do this, and then someone puts that together and builds that, and over time things build. But the enemy of the excellent is the perfect, and we've got to do whatever we can to make tomorrow that much better than we do today. But there are some things that we are dependent on as a society, and I can't imagine an alternative. That doesn't mean someday someone won't, but right now, if I could think of it, I'd be working on it.
Chemists do is find ways to connect thermodynamic, the energetics of one process to another, so that so when I teach addition and elimination chemistry to double bonds, when you add water across a double bond, it's exothermic, but if you want to make it leave, you can change the thermodynamics based on acid-base chemistry and prefer the elimination reaction. So that's part of, and that's why understanding chemistry is so, as you said at the beginning, it's the tool, it's the set of tools that we need to build to be able to address the concerns that have come up in 200 years of development of tools, of products.
One thing that's interesting is looking at physiological systems, because there is no such thing as A plus B goes to form C plus D in nature. Everything is paired with another reaction that's paired with another reaction that has a feedback over here and a feedback. And so thermodynamics get thrown out the window anytime you want to put a little box, because that box is never big enough, because this is coming in over here and this is coming in over here. So as we learn multi-systems, maybe if we're looking at a system, it's not solvable, but if it gets married to another system that no one figured out, well, gee whiz, by proximity, and you know that there's a lot of things about cogen and stuff like that isn't interesting. And so there are chemical sharing practices of the future that won't violate thermodynamics, but will expand A plus B goes to form C plus D to start looking an awful lot more like a biochemical map of metabolism. And once the human race becomes more nature-like that, then we'll start seeing these things accomplished. But it's interesting that we talk about a circular economy, but if we wanted to build a pond, what would we do? We'd dig a hole, fill it with water, throw in some fish, throw in some plants, and probably 3 months later everything's dead. Now, no ponds happen like that. What happened was over the millennia, the water came, the fish came, and everything kind of co-evolved. If we stop now and look at our factories and look at our products and somehow want to tie them together, can't. It's just not possible. That's not the way. If we could go back in time and have them co-evolve, maybe. But it's kind of too late. We can't take existing chemical enterprises and magically make them work together. So we're going to be looking in the future of how to do that and how to design things to take advantage of them when we can. But it's, like I said, there is no magic wand that has this happen overnight. We had job security for a long time. Information on my website, johnwarner.org. I'm actually in the process of getting it registered through the FDA as a cure for insomnia. If you double-click on that and you find yourself still awake in 6 minutes, you get your money back. But it has a lot of links and a lot of information to anything I talked about. That's a good place to go.
Asphalt additive, the safety and the performance are great. Are you there with the cost that we can see this start going out?
Yes.
Okay, that's neat. That's
Yes.
great.
Yeah.
And my driveway is too.
Yeah, our road used to be a
Hook
dirt
you up
road.
with someone.
Yeah.
Yeah.
Our road used to be a dirt road, and
Yeah.
then they took all the cuttings from another street,
Yeah.
spread them out on our road, now we got a
Yeah.
paved road. So.
Yeah, no,
And
it's
I don't think they used your ad.
no, I don't know. The collaborative aggregates, I'm on the sidelines as the pom-poms cheering for them. So I don't know everything they're doing, but it's fun.
In Michigan, areas where they've used fire retardant foam, particularly, in northern Michigan around military bases, now that's leached into the groundwater. And we got a real problem with that. What do you think about that area, where we use fire retardants in the past, and now they're a toxic risk to the environment?
So again, it's hard for me to come and talk about green chemistry in places where there's something just really nasty that's in the environment already. Green chemistry is let's not do that. But wait a minute, that's not saying we don't have a problem that we have to deal with. But a second order issue is oftentimes when people try to mitigate something like that, they then create yet another problem. And so green chemistry still has a role to play in how we mitigate these kinds of disasters and figure this out, because we don't want to create, the concept of unintended consequences is abundant in this field. Someone tries to solve a problem and unintendedly creates a worse one. And so these things that are in the environment already need to be dealt with, but sometimes the approach to actually try to extract them and get them out of there causes yet more problems. And so we need to be thoughtful and mindful about how to do that and mitigate those problems in a green chemistry way.
You deal with the thing about chemistry is that every molecule is its own story. So ethylene glycol will kill you, propylene glycol is food. That's one methyl group,
Right.
actually one CH2 difference. Similarly with methanol and ethanol, of course.
Yeah.
And so there is no, and this is of course why designer drugs, continue to pop out, because there is no easy way of simply looking at one molecular structure and saying this is either toxic or not.
Yeah.
And so the cost of figuring out
Mm-hmm.
what is and what isn't a problem is itself potentially a huge
Yes.
barrier.
Yes.
So that's almost more than, more of a
Yeah.
barrier than thermodynamics.
Yeah, it absolutely is, and I've got a couple comments about that.
So anyway, the
yeah.
discreteness of molecular, every molecule is its own story.
Yeah,
So,
but you know, when I was at Polaroid, we had somebody who had a computer program that before we would synthesize a chromophore, you know, they had a computer program that would predict whether it would be red, yellow, green, but more precisely what the UV spectra was. And they had 187 chromophores that were perfectly predicted by this chromophore. I would draw one, say, I'm going to make this. They would predict it. It'd be wrong. I would synthesize the molecule, and then tomorrow the program would be right, because they would change the coding. Yeah, so we have no expectation that we get it right when we design a chromophore. When, you know, the amount of money that the pharmaceutical industry spends on predictive software with the massive, massive financial incentive, if they get that right, they're not going to make millions, they're going to make billions, and they haven't got it right. So with no financial incentive, what hope do we have? The only hope that we have is the human ingenuity that I would argue right now. The EPA has 8 or 9 computational programs that are free to people to plug in a molecule and put it in. And most chemists have never heard of it and never use it and know nothing about it. If people who understand molecular structure start playing in this field and use their thought, way up. And so anything we can do to have that happen can only up the game. But you are absolutely right. That's why in another one of my, you know, magic wands, I would say that anyone who is discovering mechanistic causes of toxicity, environmental impact, if you look at it through a different way, always has a pharmaceutical application. And so, if again, what I call intellectual ecology, if we bring these thoughts together, there is a profit motive. If we could just find a way that some organization generating toxicity data has some investor that's extracting that knowledge and trying to use it for something else, maybe there can be some financial incentive to help do the right thing. I'm not smart enough to make it happen, but I can imagine it. Yeah.
Yes. Another question.
Yeah.
Quick question. So in the green chemistry, as I know, like I can use some like environmental friendly solvent, and like I would design a synthesis like use all the substance.
Yes.
I'm curious how about like the use stuff, like my clothes, my shoes. If like I use it and it's broken and I throw it away, and this is the contaminant. So. Yeah. Is this also involved in green chemistry, like people like recycle this kind of solid waste, and how is this area in industry area?
Yes.
So it's popular. Or
okay.
whatever?
So there's 2 answers to the question. Question number 1 is to get us to a sustainable future. There's a lot of work that many different people have to do. Jerry Garcia had a great quote. You know, he said, you know, people get it wrong. Everyone says, you know, do the best you can do. And he says, no, find what you're uniquely capable of doing that other people can't do, and focus on that. All right? We chemists do chemistry. And while there are social problems, there are people talking about consumption, people talking about social responsibility of reclaiming materials, of recycling, which is absolutely critical. We chemists should say, how should we as chemists be participating in this? How can we invent future textiles that facilitate reclamation? You know, when you have multiple materials stuck together, the cost prohibition is in getting them unstuck together to keep them at the same value in the commerce chain. And so if we can invent ways to anticipate, right now, everything we've invented, we invent to last forever. If we say, how can we invent it to last forever when we want it to, but trigger it not to last forever when we don't? That's kind of a new thought for us chemists, since it's a huge area that we can start thinking about. How do you design something for that eventual disassembly? That's a big role for us to play in chemistry. Yeah.
The preceding video was produced by the National Center for Pavement Preservation. More information can be found at tsp2.org. That's tsp2.org. Additional support provided by Michigan State University.